Okay then, welcome everyone. So welcome to the week 9 session of the week 9 of the week 9 of the introduction of fluid mechanics course, problem solving session. So today we will be discussing on a very important concept or cornerstone of the uh, integral formulation of the fluid mechanics, of how the conservation laws are formulated in integral form when it is required. So one of its very key feature or important element is the Reynolds transport theorem. So we'll be briefly discussing about that. So before starting, could one of you please tell me about Reynolds transport theorem? Like, what is Reynolds transport theorem? Like, if you have attended week 9 lectures, I guess Professor Chakraborty would have extensively discussed about Reynolds transport theorem. So could any one of you please explain me what is Reynolds transport theorem? Like, am I audible?
Yes, sir.
Yes. So please, any one of you, please. Augustus and Priyanka, any one of you? Yeah.
Sir,
Yeah, sure. Go ahead.
Reynolds transport theorem, we get a relation between control system and control volume properties.
Okay. And okay then. Thank you, Priyanka. So Augustus, did you attend the week 9 lectures? Am I audible? Yes. Augustus, like if you're speaking, I'm not able to hear you. Your mic is unmute, but still I'm not able to hear you. So I asked, did you attend the week 9 lectures of the Introduction to Fluid Mechanics course? Uh, it's fine. I'm not able to hear you. I guess there might be some technical issue. That's fine, no problem. You can write in the chat if there's some issue with your mic. But no problem. That's fine. Uh, Priyanka, as you have mentioned, it is a relation between the control system and the control volume properties, as you have mentioned. So I would like to ask, like, why do you think there was a need of such formulations in the first place? Like, why couldn't we directly go with the control system approach? Could you please tell?
Hello, sir.
Yeah, please go ahead.
Because in certain cases we need control volume approach. Like we can't go for control system in each and every case. If there is flow problems and all, then we have to go for control volume.
Okay, yeah, you're right. The thing is, like, the control volume approach in many cases helps us to do a simple formulation of the same problem. Like, it's not the case that if you go through the control system approach, or as it has been shown in the screen, clearly shown in the screen, that this one, if you go to the control system approach, like you follow each and every particle and try to solve its equation of motions, and try to find the net force because of each particle on a system, say, it's not that you will get a result that is not good enough. We will actually get a result that is far more accurate than the control volume approach. But still, as I have already mentioned in my previous sessions, that we are engineers, like, and as an engineer, the two factors that is most essential for us is that first is the efficiency, and second is cost effectiveness. So even if this formulation might be slightly inaccurate, but if it is cheap enough or is cost efficient enough that we can give a approximate answer or approximate value to a particular solution that we want to find, then it's good enough for us as an engineers. And as an engineer, we want that only. Like, we want a trend to know how the parameters change in a system. That's all we want, right? So that's why a control volume approach is much more popular in the fluid mechanics domain, and that's why it's clearly shown in fluid mechanics the Eulerian frame reference is a very popular one. But still, in some of research problems in fluid mechanics also, we follow the Lagrangian frame of reference when we require it, so we cannot directly neglect it. But still, because of its effectiveness and efficiency, we prefer the Eulerian frame of reference in most of the cases, as you will gradually see in the later part of the course. Yes, so yes, and that's why to transport or transform the governing equations that were initially written in the control system approach, because the control volume phenomenon or the control volume approach was not that popular enough in those times when the equation of motions are formulated. That's why to transform those governing equations from the control system to the control volume approach, we need a mathematical transformation, and that mathematical transformation is known as the Reynolds transport theorem, right? And its derivation, I guess, I would not go through it, because I guess I'm sure Professor Chakraborty has extensively gone through the derivation, and I emphasize that you go through the derivations again and again so that you get an idea how these equation or transformations are formulated, so that you can get a taste of how these equations are derived. And that's also essential as a learning in point of view of, in the learning point of view, so I also emphasize that. But yeah, that's all I guess. So again, in the control system approach, as you can clearly see here, we follow the fixed mass identity, that within the system the mass of the system won't change at all and the identity of the system would remain the same. That's the approach for a control system approach. But in a control volume approach, we select a certain volume in the flow field within which both the mass and the mass may remain conserved, but the identity of the system may change. Like the particles that were initially there may not be there after some time. Like it may be displaced by some new particles. Even if the mass of the system remains the same, it may change also. But if it remains the same, then but the identity of the system will change, because say there was a particle initially in a confinement, in a selected confinement that we choose. It may be displaced because of flow. That in say it's better if I draw it. Say this is our control volume. Say this is our control volume, and there is a flow from left to right. So initially, if there were particles, say 1, 2, 3, these particles may be displaced by particle 4, 5, 6 because of the flow. Do you get it? Like even if the mass of the system is remain the same, there are initially 3 particles and after some time there are also 3 particles, but still, even if the mass is conserved, the identity of the system has changed. Is this concept clear? The change in identity, how it occurs in a control volume approach?
Yes, sir.
Thank you,
Yes,
Augustus.
sir.
Thank you, Priyanka. Yes, thank you so much. So that's the gist of the control volume approach. The identity of the system may change, or identity of the parameters or flow may change, but the mass may remain conserved, or it may change also. So that's essential. So as I mentioned again, that it is a mathematical transformation between the control system and the control volume approach. Okay, and it is written in this form, that say if n represents an extensive property. So yeah, any one of you, can you please tell me what's an extensive property?
Dependent on mass.
Yeah, absolutely right. And then what's intensive property?
Independent of mass.
Okay, since we are discussing on these such extensive and intensive properties, could any one of you please give me some examples of extensive properties?
Momentum.
Okay, we'll eventually discuss that, but other than that, some in a thermodynamic point of view, like I guess both of you might have taken thermodynamics course in your third semesters, most probably. So in that, you might have encountered some extensive properties of a system. So could you please tell me some extensive properties? Momentum is correct. I'm not saying it's wrong, but other than that, some more.
So mass, volume,
Okay. Then.
energy.
Okay. Some more. Augustus, from your side. That's fine. No problem. And similarly, could you please tell me some examples of intensive properties?
Pressure, I think it's an intensive property, sir.
Okay. Actually, like if I recall, uh, pressure, like correct me if I'm wrong. Okay, I just have recall like pressure cannot be considered as a property of a system. Like if I'm not wrong, right? Or is it so? Like, or is it a property? I'm just confused. Forgive me for my lack of knowledge regarding it. But say I'm ignoring pressure right now. Other than that,
So temperature.
yeah. I guess then pressure can also be considered. I'm sorry. Yeah, you're right. I will just look into it. Okay, like it's very essential to know the concepts very clearly. You're right. Yeah, in that sense you're right. But I was just confused in some other when I was thinking of something else. But I'll look into it. Okay, thank you. And other than that, pressure, temperature, some more. All the specific properties, specific volume, specific energy, specific enthalpy, specific entropy.
All intensive.
Yeah, these are all intensive properties. Yeah. Okay, thank you. I guess now you have an idea of what an intensive and extensive properties are. So that's why I wanted to ask. Okay, that's clear. So here, if I denote capital N as an extensive property of a system and eta as an intensive property of a system, then eta would be equal to N by M, where M is the mass of the system, mass of the property, right? Mass of the system, or in a correct way, eta is the property per unit mass of the system. Okay, so I guess this is clear. So keeping these things in mind, the Reynolds transform theorem can be written as dN by dt of the whole system, where dN by dt denotes the complete derivative of the property of the system, is equal to the partial derivative with respect to time del by del t, and the integral around the control volume, the volume integral around the control volume, times rho n dv, where dv denotes the elemental volume of the system. Okay, and eta is the intensive property, plus surface integral along the surface of the system, where n integral of rho eta in bracket vr dot n cap, where n cap denotes the normal vector of the area along which you are doing the surface integral, and dA, which denotes the elemental area of the system. Okay, and Vr here is the relative velocity, which is the relative velocity of fluid respect to the control volume. Okay, don't confuse yourself with eta and n cap. Okay, eta is the intensive property and n cap denotes the normal vector, and in general it is Vr dot n cap and not V dot n cap. Okay, Vr is the relative velocity, and within some certain assumptions only we can write Vr. We can write Vr equal to V, only under certain assumptions. Okay, which will gradually look through it. So is the formula clear? Is all the terms in the formula are they clear, or do you have any doubt in the formula?
Yes, sir. Yes.
Thank you.
Yes.
Because see, it's a very essential, very integral part of all the fluid mechanics problem that you're going to solve after now. Like after this, each and every fluid mechanics problem could be approached by a perspective of Reynolds transport theorem. So it's very essential for you to know how to apply it, when to apply it, and how to choose the control volume or the control surface, right? These things are very important. So, and also the formula, like whether it is relative velocity or the absolute velocity, that things you need to be very clear. So that's why I was asking. So it's clear, then it's fine. Again, we will go through some examples. So I guess that would make the concepts more clear. Okay. So as I've also mentioned here, that the control volume that we choose may be may be deformable and moving, right? We have no restrictions over this governing this initial formula Reynolds-Armstrong theorem, that here the control volume may be moving also and may be deformable. So these two restrictions we have not put yet in the in this formulation. So this a very general form, the most general form of the Reynolds transport theorem. Okay, so yeah, so before looking into the conservation of mass, I would like to just say ask some questions, or just like to, out of curiosity, I would like to know, like I guess you might have heard about the continuity equation, like we have used in fact in our formula in our problems, in our previous problems. So could anyone of you please tell me the formula continuity equation? Or what is continuity equation? Like, could you please tell me the at least the mathematical form? Yeah, please go ahead.
Continuity equation is for mass conservation.
Okay, no, that I know, but could you tell me the mathematical form? What's it? What is it?
Rho A1 V1 is equal to rho A2 V2.
Okay, Augustus says rho A1 V1 is equal to rho A2 V2. Is the density different or the same in this formulation that you are telling? Because if they are same, then we can just
Density is same.
same. Then we can just remove it, right? There's no point of writing rho A1 V1. Then we can just write A1 V1 equal to A2 V2. Okay, this is what Augustus says. What about you, Priyanka?
So dou rho by dou t plus del of rho v.
Del, is it a gradient or divergence?
Gradient. Del dot rho v
That only.
is equal to 0.
Okay. So it is 0, right? This is one form. This is another form. So I would say both of you are correct. Augustus has just told in an integral form with certain assumptions in his mind. After taking certain assumptions only, we reach a simpler form of the continuity equation. This is a very simpler form of the continuity equation, and it is still valid. It's not that it's wrong, but it is been derived after taking some certain assumptions. Okay, and this, what Priyanka has told, is the differential form of the continuity equation. This is also correct, but again this is a differential form. If we go into look into the integral form, it will have some different form, like there will be some difference, like because after taking certain assumptions from the integral form only, we can say that we look through it that the integrand is equal to 0 because the integral is 0, and that's why we can say that the integrand is 0 and the integrand it's not the integral, okay, the integrand turns out to be 0, and that's why the integrand, where the integrand is this one, which gives the differential form of the continuity equation. Okay, so as you have rightly mentioned, it gives it tells us about the mass conservation, and like I guess in the first class or in the first session itself, I have told that any fluid mechanics problem could be approached by three conservation and like any fluid mechanics problem should adhere itself to the three conservation laws. So what are they? Could you please tell, if you recall?
Mass, momentum, and energy.
Okay. Momentum, is it only linear momentum or angular momentum as well?
Both.
Okay, thank you. Okay, so I will write conservation. So any fluid mechanics problem should adhere itself to these three conservation principles, and you can as a clue or as an idea of approaching problem, I can say that given any fluid mechanics problem, you can approach it by these three conservation principles, and nobody can say that you have done a wrong approach, like your approach was wrong, because all the fluid mechanics problems that have been designed, sorry, all the fluid mechanics that have been designed till now has built this foundation with respect to these three laws itself, right? So any concept that you write with respect to three laws, these three laws cannot be wrong at all. So say you are given a problem and you are trying to approach those problems with respect to these three principles, you are going in the right path. And it is just the further mathematics or the further tricks that you need to solve these problems that will give you the rest of the marks. Say you are given a 10 marks question, say a very difficult fluid mechanics problem you are given, and you have written these three governing equations and tried to resolve the parameters with respect to these three conservation laws. You will at least get 5 marks, because you know that this 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 mass molecular energy must be conserved whatever may be the fluid mechanics problem. So given this idea, the examiner or the one who is going to check your answers will know that at least you have an idea how to approach a problem with respect to these three laws, and that's why it's very essential. And how the governing equations for this law, for these conservation laws are derived, it can be done to various ways, but one of the efficient way is through the help of RTT. Okay, and that's why RTT is very essential, because once you know RTT, you know how to derive the conservation laws, and once you know the conservation laws, any fluid mechanics problem is tractable. I will not say solvable, completely solvable, but at least analytically tractable. At least you can write an approach that, yeah, this problem can be approached by the help of these conservation laws. So you are going the right path, and that's why you are at least having a right approach to the problem. So is the idea clear, like why it is very important, RTT?
Yes, sir.
Yes, thank you.
Yes, sir.
Yes, so it's very important for you. That's why I'm giving so much time or emphasis on knowing the importance of RTT, is because after a student knows RTT, none of his fluid mechanics problems he will get 0 marks. Like he will get some marks because at least he knows the approach to solve a problem. That's why I wanted to share this trick, or what to say, an essential idea before going through the derivations. At least you are motivated enough right now to go through the derivations. That's why. Okay then. So given that idea of mass conservation, as I have already, as you both of you rightly pointed out, mass conservation also can be derived through various ways. Like the concept remains the same, but the derivations can be different. If you go to different fluid mechanics books, there will be different ways of deriving the mass conservation, and one of the way will definitely be the RTT, and we will go through the approach where RTT is used. Okay, so here in this equation, say I name it equation 1 or equation star, because it's very essential. So from equation star, if I replace capital N by M, where M denotes the mass, then what would eta be? M by M, that will be equal to 1, right? So once I replace this, I get an equation of this form: del by del T integral over the control volume rho dV plus integral over the control surface rho in bracket VR dot n cap dA. And why dm by dt system is 0? Could you please tell?
Because in the system, identity of particle is fixed.
And the mass also remains the same, right?
Right.
Yes. So given that conservation of mass, we can say that dm by dt of the system would remain 0, but for a control volume in the, at least in the right hand side, we have some terms, and these terms are these terms are like these are terms, and this will be equal to 0. So keeping that in mind, okay, let me just write it. Next is a problem, and I guess I will not go through that problem. It has been discussed in the class itself. So this is again a very general form of the mass conservation without any assumption. At least till now there are no assumptions made. It's a very general form of the mass conservation, and it is in the integral form. Okay, integral form of mass conservation. Okay, so this is the integral form of the mass conservation. Okay, so this was a problem. I guess sir has gone through the problem in the tutorial, in the lectures, but still, just to see how to apply, just an example. Let us go through this example. So yeah, say this is a system. Okay, this is our system. It's a spherical chamber where you are blowing air in, and where it basically you can consider it as a balloon where you're blowing the air in, so that the volume of the balloon will change with time. Like once you start blowing in air, the volume would go up, right? The volume would increase because the pressure inside the balloon will increase, will be greater than the atmospheric pressure, so it will deform and it will increase its volume. So what we are asked is, we are asked to find the rate of change of balloon with respect to time. Okay, see, from now on, you need to know that V cut will denote the volume and straight V will denote the velocity in vector, obviously, but still, to be very clear, V cut will denote volume and V will denote velocity. So right, so now we apply mass conservation. So say from the start itself, you write del by del T. Okay, sorry, I forgot how to write forgot to mention how to choose the control volume. So here they have chosen a control volume in this pattern, like a control volume surrounding the balloon, and just the inlet where the air enters. This is the choice of the control volume. So is there any other, according to you, like, is there any other way by which we can choose the control volume?
We can take a control volume including the inlet.
Okay.
Pipette.
So yeah, I guess that's correct, because that won't change the physics of the problem much, but this is also correct. Okay, and you will eventually see that an ideal choice of the control volume is where the velocity profiles are known to us, like most of the velocity profiles in the problem are known to us. And since here this is a very simpler version of the problem where we are not considering, I guess we are not considering viscosity or at least the velocity profile inherently, so it's a very simple problem. So whether you choose the control volume here or here doesn't make much of a difference. So this is a very simpler case. So the choice of control volume remains open in many ways, but still an idea of choosing a proper control volume helps us to simplify the problem a lot. So you will get to know this once you start solving various problems. So just as an idea, I mentioned it. Okay, so writing the mass conservation principle. So is rho del V plus integral of control surface rho VR dot nk d. Okay, so here equal to 0. So So I guess here they have mentioned in the problem they have mentioned that the row remain uniform property. Yes, right, they have mentioned the property remains same within the volume, and that's why rho is not dependent on the surface dependent on the spatial coordinates. Okay, and that's why we can directly take rho out of the integral. Okay, I will simplify this one also. So yeah, is this approximation clear? How I have taken rho out of the integral?
Yes, sir.
Okay, because rho does not depend on the spatial coordinates. As I mentioned that the properties within the balloon remains the same. Okay, and this one basically denotes the mass flow rates, like mass flow rates at the inlet and outlet. Okay, because like if you check the dimensions, you will find that this will basically be equal to rho AV, which basically means the mass flow rate at the inlet and the outlets. Like here in this case, this is a special case where there are no outlets and there are only one inlet. So here it will be like if I write in the mass flow rate form, like since the velocity profile is not known and velocity profile is not known, and we can just ideally assume that the velocity profile remains uniform considering an inviscid case. So we can say that this would basically give us the mass flow rates at the inlet and outlet. Okay, the difference between the mass flow rates at the inlet and outlet. So with the sign convention, what would be the sign convention for the outlet? Like would it be positive or negative? That VR dot n cap at the outlet, would it be positive or negative?
Positive.
Okay, right, because if there would been an outlet, say in this case, like this outlet and the velocity is in this direction, if it's essentially is in this direction, and the normal vector of this area, say, it also point in the same direction, and that's why the dot product of v dot n cap will give v directly, right? There is no negative sign because if the v dot n cap basically means v n cos theta, right? Say if theta is equal to 0, basically an n cap is a unit vector, it will basically give us v. Similarly at the inlet, since the normal vector since the velocity, the direction of velocity and the normal vector are opposite to each other, it basically means v dot n cap cos 180 degree, and cos 180 means it is -1, so it will essentially give us minus v, and that's why at the outlet we have the mass flow rate will have a positive sign. That's why we can write m dot out minus m dot in. You get right why we make the minus sign?
Yes, sir.
Yes, because of the sign conventions of the normal vector and the velocity vector. Since they are opposite, that's why we get a negative sign, and that would be equal to 0 again. And since m dot out is equal to 0, as you can clearly see, it is 0. That's why we will have only del rho by del t. This will, I guess, directly give us this integral will directly give us the control volume, the volume of the control volume that we have chosen. So we can write it as VCV minus m dot in is equal to 0. So we can write del by del t of rho VCV is equal to m dot in. So this is a certain, this is a correct, this is a certain step of the solution that we can obtain. Like this is also correct. And if you were to simplify it further, like as Professor Chakraborty has used, assumption that if we assume that rho is not a function of time, then we can directly take this out of the directly take rho out of the integral, so it will become rho del VCV by del t is equal to m dot in. And again, if they mention that since the properties remain the same within the volume, the control volume, we can say that with respect to spatial coordinates the volume does not change, and that's why V depends only on time. That's why instead of del by del t, we can directly write rho, the complete derivative, dvc by dt is equal to m dot in, where it gives us dvcv by dt is equal to m dot in by rho. Is it clear up to this point, like how we obtained it, how we have taken the assumptions, the steps? Is it clear?
Yes, sir.
Yes. Again, so I have one doubt. Like Professor Chakraborty have rightfully mentioned that rho is not a function of t is a very bad assumption. So could you please give me an please tell me why this is a very bad assumption?
Because here we are considering air, it is compressed.
Yeah, and what about the problem? With respect to the problem, like blowing air into a balloon, does it have significant change in density within the control volume with respect to time?
It will have.
Yeah. Yes, you're correct. In a sense that the rate at which the air enters the balloon is much higher than the rate at which the volume of the balloon changes with respect to the spatial coordinates. Like I'm just giving an idea or the order magnitudes of the changes. In that respect, you can say that since the rate at which the air enters the volume is much higher than the rate at which the volume of the balloon changes with respect to spatial coordinates, you can say that there would be a significant change in the density of the air within the balloon with respect to time, and that's why this assumption is very inaccurate. We can say very inaccurate. But for a simplified case, like if it is given in a problem for you to take rho is not a function of rho t, you can take it, but it's a very vague or very inaccurate assumption, and that's why Professor Chakraborty has rightly pointed it out. And these are some of the logics that you should keep in mind before implementing or taking before taking some assumptions. Okay, like you cannot directly take rho is not a function of rho t, like if the problem is given like this. So you need to write that I am making very inaccurate assumption before taking this, so this approximation, so that's why I'm getting this answer. So this again a very inaccurate answer, but you can get a trend of variation of the change in the volume of the control volume respect to time. Very inaccurate inaccurate results, but you can get the trend, so you get an idea, right? How we can get the solutions, whatever solution we get by applying this RTT. So you get a slightly inaccurate results, but you can get the trend of variation of the properties, and in that sense RTT is very essential. So this is one of the example. And again, okay, yes, so this is again the very general from the mass conservation, no assumption taken right now. So now we take some certain assumptions. Okay, so please focus to it. Like if you have any doubt, you can ask me. Yeah, so the first assumption they have taken is that a non-deformable control volume. Okay, they have assumed that the control volume that we are considering does not change. Okay, in the previous case the control volume was deformable. Okay, and that's why there was V was a function of time. Okay, V changed with time. But now we have explicitly mentioned that it is a non-deformable control volume, and that's why the volume of the control volume does not change with time, and that's why we can take this time derivative inside the integral. Okay, we take this time derivative inside the integral, and after taking that we get this form. The second term remains the same. There's no change in the second term because of this assumption. Only the integral, only the derivative can be pushed inside the integral. So this is first step. And then the second assumption that we take is a stationary control volume. Like if we take the assumption that the control volume that we have chosen for our solution is stationary, that it does not move along with the flow or doesn't have a certain velocity, then the velocity by which the fluid comes out of the control volume would be equal to its relative velocity, right? Would be equal to its absolute velocity. So VR would be equal to V. And in that sense only we can write here the absolute velocity of the fluid flow instead of the relative velocity. So is this clear? Like the second assumption, especially the second one, is that clear?
Yes,
Yes, sir.
Yes, okay. Say I have chosen a control volume. Say I'm giving an example. I have chosen a control volume which moves in the flow, which has a velocity equal to the velocity of the flow within the control volume. So what would be VR in that case?
0.
Okay. So this would essentially mean that there's no mass flow rate out of the chosen control volume, right?
Yes, sir.
Yes.
Yes, sir.
Yes. Just asking so that it's clear. So it seems it is clear. So this is very important. Okay. So you will encounter some cases where you have to choose a moving control volume, and then you need to keep in mind which velocity to choose. Like you might have a velocity that is the intensive property that you are going to conserve, and within the brackets the inherent term of the RTT, there is a relative velocity instead of the absolute velocity. So whether it is V or VR, you need to be very sure. Okay, here it's only mass conservation, so you are not getting any intensive property to conserve. The intensive property is one itself, but as we go to the conservation of linear momentum or other properties from now on, you will have some inherent intensive properties that you are going to conserve within the these governing equations. So that's why you need to be very sure when it is V and when it is VR. So these values need to be very clear. That's why it's very important for you to know the difference between the where VR is used and where V is used. Okay, just giving you an overview. Eventually you will encounter such problems. Okay, so this is so this is the final form of the equation after implementing these two assumptions. Okay, a non-definable control volume and a stationary control volume. So now okay, so I guess you know Gauss divergence theorem. Like you might have encountered in your vector calculus course or mathematics course where you have read vector calculus. So you might have encountered this form of the transformation, which is known as the Gauss divergence theorem. Okay, and again I guess Professor Chakraborty rightly pointed out, emphasized for us to know that the surface should enclose the entire volume that you are considering. Okay, so given this, we can write the Gauss divergence theorem where it says that the surface integral of f dot n cap dA would be equal to the divergence of the vector field, the volume integral of the divergence of the vector along along the chosen volume. Okay, so this is the Gauss divergence theorem. So implementing Gauss divergence theorem in this term, in the second term of the mass conservation, we get that this will transform into a volume integral. So you can write it as you can write this as volume integral of divergence of rho v dv. Is that correct?
Yes, sir.
Yes, thank you. So keeping that in mind, we can then write this equation, and we can, since the volume that we are the elemental volume with respect to which we are doing the integral is the same, then we can just take the integral sign common for both the terms, and write the integral in this form. Okay, so again sir has emphasized that this integral will only be 0 when the integrand is 0. So for the integrand to be 0, we need to have del rho by del t plus the divergence of rho v equal to 0, which is the mass conservation in the differential form, as Priyanka pointed it out when I asked for mass conservation. She rightly pointed out it is the differential form. And again, if you look into here, say this form, the most general form, okay, this one. Say if we take an assumption of steady flow, say that if the flow is steady flow and rho is constant, okay, these are two assumptions I have taken. Then the first term will go out, right? The first term will equal to 0. Is it clear?
Yes, sir.
Yeah, first term will be equal to 0, and the second term will have rho out, so it will be that it will just be rho of Vr dot n cap dA equal to 0. So it will essentially give us surface integral of Vr dot n cap dA equal to 0. So it will essentially mean this term essentially gives us the volume flow rate. So it will, since rho is constant, so we can write it as Q out, keeping in mind the signs of the normal velocity vector with respect to normal velocity vector with respect to the velocity vector with respect to normal vector of the areas along which we are evaluating the surface integral. So it will give us Q out minus Q in equal to 0, or more accurately, I'm sorry, I should write it as summation of Q out minus summation of Q in would be equal to 0. So it would essentially give us summation of Q out is equal to summation of Q in. So if there's only one inlet, there's only one inlet and one outlet, okay, so it will give us Q out equal to Q in. So we can write this, say it is with respect to 2 points like 1 and 2, say, then you can write A1 V1 equal to A2 V2, which is essentially what Augustus has mentioned as the continuity equation. So is that clear, Augustus, how we obtain this form of the continuity equation after taking certain assumptions?
Yes, sir. Yes, sir.
Yes, you get out of the integral form, right? If it is steady flow and the density of the flow remains constant. So after, only in that case we can say A1 V1 equal to A2 V2. Okay, so I guess this is clear up to this point. And yeah, again, as Professor Chakraborty rightly mentioned, a good choice of a control volume is the one across which we are totally confident about the velocity field. So it is a very essential point, and I emphasize both of you to be very clear while selecting your control volumes for solving different fluid mechanics problems. So you should only choose the control volumes across which you know the velocity field, right? I guess sir would have taken an example where there was a container which had two arms, where one was inlet and one was outlet, and sir also showed that if you chose a control volume in a separate way, I guess I have in my notes. Sorry. No class coming. Okay, I'm sorry. So I don't have it right now, but I guess he had taken an example of this form, say, right? If you recall your video lectures, this was the problem, I guess, where he has given the velocity profile here and here. He said it is uniform, and asked you to take the control volume in this form. Sorry. right? And also emphasize you that you cannot take a control volume. You can take a control of this form, but you need to know the velocity profile at these points, right?
Yes, sir.
Yes, but since you do not know, or you're not sure how the velocity profile would be at these points, there is no point of applying RTT in this, having this control volume, because you do not know the velocity profile at these points, and that's why a right choice of the control volume would be the one with the enclosing the inlets and both the inlets and the outlets where the velocity profiles are known. That's why he took this example, and I also encourage you to solve such problems, different problems where you need to choose, what to say, intelligently choose the control volume so that you can get an idea of implementing RTT in a most efficient manner. Okay, so yeah, and I guess he has also briefly discussed about the conservation of linear momentum. So as Augustus has rightly mentioned, the momentum to be one of the extensive properties. So here, what would n be? Capital N.
MV, sir.
mv, where v is a vector, and eta would be the velocity vector v, right?
Last.
Yeah.
Yes,
So
sir.
from implementing this in the RTT, we can write it as d by dt of mv, where mv denotes the linear momentum of the system, is equal to the partial derivative del by del t, and with the volume integral over rho, volume integral of rho v dv, where v is where eta is now substituted by the velocity vector v, and again here eta we substitute eta by velocity vector v. So here first term is there, and second term would be the surface integral of rho v, where v is the absolute velocity of the flow field, multiplied by vr dot n cap dA. And again here see, here it is v and here it is vr. Okay, it's very important to know where it is v and where it is vr. Okay, and where it will both be v. Where do you think here we can write the second term as, in which case do you think we can write the second case as rho v dot n cap dA? In which case do you think we can write the second term in this form?
Stationary control volume.
Yeah,
Station.
absolutely correct. So if the control volume that you have chosen is stationary, we can write vr is equal to v. So our second term would be of this form. Okay. So I guess Sir has discussed up to here only, and he will discuss more about this in. I guess he had discussed already if you have watched the week 10 lectures. So he's discussed. So I guess for week 9 only we are confined to these concepts only, and now we can look into the problems. So yeah, so let's go to the problems. They are very simple problems. So I encourage you, both of you, to try to solve and tell me the answers. Okay. So this is question. Okay, I'm sorry. This should be week 9. I'm sorry. So okay. So this is question number 1. Let me read it. Okay. Water flowing through an 8 centimeter diameter pipe enters a porous section, as shown in the figure below, which allows a uniform radial velocity VW through the wall surfaces for a distance of 1.2 meter. This distance. Okay, let me zoom it a bit. Okay, if the entrance velocity V1 is 12 meter per second, find the exit velocity V2 if VW, that is the velocity across the porous section that they mentioned here, is 15 centimeter. Okay, 15 centimeter per second out of the pipe walls. So is the question clear? Okay, let me.
Yes, sir.
Okay,
Yes, sir.
in a 3D perspective, it basically means that velocity enters here, the flow enters here, it goes out from here, as well as say a section within this pipe where it is porous. Say there might be some pores or some holes through which the velocity, like as an approximation, they have said that the velocity is uniform and the flow goes out of these pores as well, which has a velocity of 50 centimeter per second throughout the surface of the cylinder or the pipe. Since it is pipe, so we can take it as cylinder. So yeah, so I guess the question is clear. So given that, you need to find the exit velocity v2. So it's very simple. Again, I will give you some time to solve to try to solve this problem. It's very simple application of mass conservation. You need start from the complete formula mass conservation, remove the terms after applying certain assumptions, and find the required parameter. Okay, it's very simple. See the terms: uniform velocity, average velocity. Why? It helps to take certain simpler forms of the volume flow rate. Instead of integrating, you can directly write it in terms of a1 v1, even if certain terms are mentioned. Say if average velocity is mentioned, you can directly write it as the area into the average velocity, because the very concept of average velocity comes out like this, like so. Yeah, it's very simple addition and subtraction. What goes in should be equal to what goes out. And the geometry itself should give you an idea that okay, there should be no storage term, as well as you can take a simplified assumption that the flow is steady. So since they have not mentioned that the flow velocity is changing with respect to time, okay, it's also very key feature, and the geometry itself should give you an idea it is a steady flow. So given these simplifications, I would say the mass conservation becomes very, very simple. So tell me the answer. Check the units. Okay,
Sir,
option A. Okay, 3 meter per second. This is one of the answers. And what about you, Augustus? Do you get the same answer? That's fine. Augustus can continue, but okay, Priyanka, could you please tell me what was the, at least the form of the steps, some of the steps of your solution?
so using conservation of mass,
Okay.
since it is steady flows, the first the dou by dou t of rho VCV will be 0.
Okay.
So it will only be the control surface.
Okay.
So
Surface
mass
integral. Surface integral.
surface integral.
Okay.
Surface integral.
Yeah.
So it will be mass flow rate inlet is equal to mass flow rate outlet.
Okay. So what is m dot in?
M dot in is minus 12 into area pi d square by 4.
Are you sure about the minus sign here? Even after you have written it as m into m out, are you sure about the minus sign here?
In the equation, I wrote it as m out minus m in.
Yeah, it would be equal to 0, and that's why this sign will go cancel out,
It
right?
will be positive.
Yeah,
Yes, sir.
yes, sir. Very important to be careful about the sign conventions, right? So,
Yes.
okay, would be equal to what?
Equal to VW, that is 15 centimeter 0.15 meter per second into pi into 0.08 into 1.2.
Basically the lateral surface area of the cylinder, and some other term
Plus V2.
right?
Yes, sir.
Okay. So Augustus, did you get the same steps while solving the problem?
Yes, sir. Yes, sir.
Did you get the same answer?
Yes, sir. I got it, sir.
Okay. So since both of you have got the same answer, and since the steps are correct, I can say 3 meter per second is the right answer. But again, see, there are certain terms that they have mentioned here, because of which you were able to simplify this term in terms of only, say, m in minus equal to m out, and that also you have taken it directly as rho 1 a1 v1, sorry, rho in a in v in. Okay, why you could take it? Because they have mentioned that the entrance average velocity is v1. They have not mentioned any velocity profile here. Okay, they strictly told it it's the average velocity. So if it's the average velocity, then you know that the mass flow rate, sorry, the volume flow rate could be essentially be written as the area A into the average velocity Vm. It's an essential concept that you will eventually know when you go to the later part of the course, or I think you might have gone through it, but still you should know why you're able to write it in this form and just ignore the integral sign completely. It's not that it's not equal to this, it is not that this is not equal to this, but why this integral was simplified so much. Okay, because velocity profile is not mentioned, and they have told it is the uniform velocity. Okay, so average velocity, again they have told it is a uniform radial velocity. They have not mentioned any velocity profile. Okay, and that's why you could have directly take you can directly take it as 0.15 meter per centimeter, sorry, 0.15 meter per second. Similarly for v2. So given this assumption only, you are able to simplify the second term of the mass conservation. Okay, so these things you need to keep in mind, because this concept will come out in handy. Okay, so right, so the second question is again exactly the same. If the entrance average velocity is now v1 is equal to 12 meter per second, now find the exit velocity v2 if vw is 10 centimeter per second into the pipe. Now they told that the flow is going inside the pipe instead of going out. Okay, I again, for saving time, this equation will remain the same, just the signs will change. Signs and the values of the velocity will change. Please do the certain the concerned modifications and tell me the answer. It's very simple. Just the signs will change. Now the velocity is inside the pipe through the pores. It's not going out, it's going in the pipe.
Sir.
Yeah.
C.
18 meter per second.
C.
Augustus, is it the same for you? Oh, you can take your time, no problem. did you get the same answer, Augustus?
So first term is 12 instead of 10.
17.9, 18 meters per second.
Yeah. Thank you to both of you for correcting me again. I'm sorry, I took this 10. Thank you, Priyanka. Thank you, Augustus. Both are correct. So 17.9 basically means it's 18. So thank you. Okay then.
Thank you, sir.
Both of you are correct. So let's go to the next question. Okay. Now it's interesting. I was discussing only about the if the velocity profile is given, the second term would not be simplified. The same question has come. Water flows steadily, again essential key terms, steadily through a pipe of length L and radius R is equal to 75 millimeter. Calculate the uniform velocity, inlet velocity U, uniform inlet velocity U, if the velocity distribution across the outlet is given by U equal to U max 1 minus R square by R small r square by capital R square, where U max is equal to 3 meter per second. They are given the coordinates, how the coordinate system is here. So it is R in the radial direction and X along the axial direction. Okay, and capital R gives the radius of the pipe. So basically it's a pipe again, so cylindrical coordinate systems. So keeping that in mind, okay, again one clue, it's a cylindrical coordinate system. So since it's cylindrical coordinate system, now you need to know how to take the elemental surface area, right? So cylindrical coordinate system. Okay. Steady flow. Okay. Same steps, mass conservation only. Now you need to know how to do the integration at the outlet and take the correct elemental surface area. Sorry. Any progress? Both of you are doing it, right?
1.5.
1.5. Okay, that's one of the answers. And okay, this is one of the answer. And Augustus, like, did you also get a similar answer? Okay, Priyanka, could you please tell me what you have chosen the elemental area, like dA in this case?
2 pi r dr.
Okay. Okay. Since it's a cylindrical coordinate system, you have correctly chosen the elemental area. So this is a gist of the problem. To choose rightly choose the elemental area. Okay. So that's fine. So I cannot solve it here since it's a bit long. The integration part is a bit long if you're doing it like entire integration. So I'll just show it the solution part. Okay, so this is the diagram, this and the given values of the parameters. So again, by mass conservation, we can write q in is equal to q out. Okay, I'm sorry again, I directly gone through the solution without asking Augustus. So Augustus, did you make any progress? Like, have you gotten the answer?
No, sir, I'm sorry. I would like to see the concept.
Oh, sure, no problem. Okay, let's go to the solution slowly. Okay, so yeah, you at least know how we got q in equal to q out, right?
Yes, sir, yes, sir.
Because the flow is steady and property, like, since they're not mentioned that the density is changing, and you should also know by idea that the density only appreciable density change only takes in a compressible flow regime. So since flow through pipes are generally incompressible, so density essentially remains constant in this case. And if they mention water, yeah, if they mention water, it essentially remains constant. Okay, so density remains constant. So keeping that idea in mind, we can get q in is equal to q out. Okay, then we can write q in as u pi r square. Why u? I have written directly because they mentioned that the velocity profile is uniform. Okay, yes, and then at the outlet we have this term, right? We essentially have vr dot n cap for dA. So it will, since vr is the absolute velocity, n cap is the normal vector, unit normal vector, and since there is no, in this case at least, since there is no angle between the area vector and the velocity vector, so it will essentially give us v of r dA here. Now the key is how to choose dA. So do you know why you have chosen it as 2 pi r dr for the given problem instead of, say, dx dy?
Yes, sir, because it's a cylindrical pipe we are chosen there.
Yeah, right. So since you know that, then we can directly write it. Yeah, integrate it. Sorry, integrate it. So it will be u max 1 minus r square by capital R square 2 pi r dr. So we take all the constants out. 2u u max are constant, so we take it out of the integral sign, and integration will be from 0 to r. Okay, so once we do integration, we get r square by 2 minus r to the power 4 by 4 capital R square. Once we substitute the limits of the integration, we get the right hand side as 6 by r square by 4. So we equate it to the left hand side, we cancel out some certain terms. So after that, we finally get the uniform velocity u is equal to 1.5 meter per second. Okay. Okay, you can ask doubt if you have doubt in any of the steps.
Yeah. Yes, sir, I understand it.
Oh, I understood it, right? Okay then.
Yes, sir.
Thank you. So let's go to the, I guess Priyanka also followed similar steps, right?
Yes, sir.
Yeah, thank you. So thank you. So let's go to the next problem. This is a very interesting problem again. Flow of problems of bent pipes. Okay. Water enters a two-dimensional square channel of constant with h. Okay, they have mentioned again it's a constant with h, where h they have given as 75.5 millimeter with again a uniform velocity u. So they mentioned that the inland velocity is uniform again. Okay, and essentially drawn it like that itself, uniform velocity profile. The channel makes a 90-degree bend that distorts the flow to produce a linear velocity profile as shown in the exit. Okay, linear velocity profile. Now it's not uniform. Okay, it's a linear velocity profile at the exit with Vmax is equal to 2 Vmin, Vmax and Vmin. Okay, now we need to evaluate Vmin if u is equal to 15 meter per second. U is 15 meter per second. So it's a, I will not say very tricky problem. It took me also some time to solve, but it's again a bit complicated problem respect to the previous ones, because now it's a bend in the pipe. So you need to choose the control volumes again and then apply the concerned conservation principle. Okay, so is there any doubt in the question?
No, sir.
Okay, thank you.
No, sir.
Okay, then I'll just say choose the correct control volume, apply the conservation principles, whichever you might need, and find Vmin. Okay, so take your time.
Sir, C 7.5, sir.
Okay, 7.5 is one of the answer. Okay, we will wait for Priyanka also to give her answer, then we will look at the solution. Okay,
Okay, sir.
sure, thank you.
Sir, I think I did a mistake. I got 10.
10.
Yes.
10. Okay. So, okay. Say I also don't know what the solution is. So let's ask Augustus first. So how did you approach the problem? We'll see both of your answers, at least the steps here, and then see who is right, who is wrong. Okay. Since you are getting for the first time here today two different answers, but still it's fine. Let's see your approach, Augustus first. Could you please tell me how you approach the problem?
Yes, sir. I made a simple approach only. Yes, sir. I mean, Q in, I equated Q in to Q equal to Q out. I
Oh,
don't know whether it is correct or not.
Q in
So
equal to Q out.
V,
Okay.
yes. So V minimum into 4H is equal to V max into 4H.
Wait. V minimum into 4 uh,
H
4h, so
is equal to
is equal to
V max into 4H.
okay. Okay, let me ask, since I'm also very confused. So where does this 4h term comes? 4h, how do you get this 4h term?
It's a constant with the square channel, no sir. So the cross-sectional area I took as 4H.
Okay, but for area of cross section of a square channel would not be 4h, right? It would be h square, right? Its perimeter is 4h, but area
Yes,
is
yes, yes.
h square. Okay, then I think and also why you have
Yes, however, it gets cancelled on both
yeah,
sides.
no, that's fine,
Yeah.
but how did you get it as v min into v max? Like at the inlet it is not v min, right? At the inlet it is let me
At the inlet, sorry, in the inlet it is U. So I took it as U A squared. U A squared is equal to V max A squared.
this one,
Yes, sir.
but here then you will okay, then you get v max.
Then V max I substituted as a 2 V min.
Basically you will get v max equal to u, then it will get 15 meter per second, right? uh,
Yes, sir.
then v min would turn out to be 15 by 2, so it will be 7.5. So
Yes, sir.
this was an approach, but again let me tell you, like why did you choose the outlet velocity as vmax? That's my question. This is fine, but why this?
Because it is given in the problem, no, sir, that distorts the flow to produce the linear velocity profile shown at the exit with V max equal to 2V.
Yeah, but they have told it is a linear velocity profile, right? It is not uniform. So this you get this one, right? Cs vr dot n cap dA, and even if you have the normal vector in the same direction, so you will get it as v of x in this case, then dx into then h terms, if we assume that which remains constant, uh, since the square generates, it will obviously be h, then the cs term. So it will be something like this, and you need to actually find out the velocity profile vx. Okay, that was the gist of the problem, right? So don't mind, I will mute you for some time. uh, there was some issue with your mic, I guess. So you just listen to me, like after you can unmute and tell me the answer. Okay, so the thing is that you need to find the velocity profile along the x direction, because you can clearly see here, since the 90-degree bend, now the velocity profile varies with the x coordinate. Okay, and that's why you need to find vx first, do the integration, and then equate it to the inlet velocity profile, the inlet volume flow rate. Okay, so yeah, Victor, now you can speak. Like, did you get the concept? Where you did mistake?
Yes, sir. Yes, sir. I got it, sir.
You need to find the velocity profile at the exit, because it's not a uniform velocity right now, it's a linear velocity profile. The velocity varies linearly, and that's why you need to find the velocity profile. Okay, since you know where you made the mistake, and that's why this answer is not wrong, but still I appreciate that you have tried and you have done on the mistake only at the last step, so that's fine. but you need to check in the future questions. Okay, so keep that in mind. Again, okay, thank you. So Priyanka, now could you please tell me how did you approach the problem?
I found the velocity profile at the exits first.
Okay, tell me the approach.
Velocity profile at exit I got as V minimum plus V max minus V minimum whole bracket into X by H. No, sir. Not the first one. V max minus V minimum whole bracket X by H.
This one.
Bracket is at for the not the first one, sir. V minimum. V minimum plus bracket.
This one, right?
Yes. Yes, sir.
Okay, so after you substitute this in the in the velocity profile, you get v is equal to 10 meter per second, right?
Yes, sir.
Okay, say I actually don't know whether it is whether this is the right one or not, because I have got the same answer but a different solution. So either of us could be wrong. So that's the funny part. So I don't know, but the answer is 10 meter per second. So let me okay, could you please tell me how you found out the velocity profile? That would be interesting. Yeah.
Sir, using similar triangle approach I found, sir.
Great. So I guess
I divided it into two parts. One is rectangle and one is triangle.
like this.
Yes, sir.
Okay, then
Then it will be V minimum plus, since the rectangle is uniform part, so V minimum plus the triangle part. In that I use similar triangle.
which are the two triangles that you have chosen?
One triangle, so the top one. In that I just took one section X somewhere.
Like this?
Yes, sir.
Okay. So essentially you found out the equation of this straight line, right? I guess.
Yes, sir.
Yes. So I also essentially did the same thing. So it's very great that you have found the answer with a different approach. So it's very appreciable. So very good. And Victor, like I encourage you to look at both the approaches. She has used the approach of similar triangles. That's also correct since she has got the right answer. So let us look into my approach also. So this is the problem. So again, as you have rightly pointed out, Victor, that the first term would get cancelled out, so only second part of the mass conservation would remain since it's steady flow, and rho is also constant they mentioned. So you get integration of vr dot n cap dA is equal to 0. Okay, so at the exit would be positive sign, so integration of 0 to h u of x dx h. Why u of x? Because the velocity here varies with respect to x, right? So it will be a function of x. So it is u of x dx dot h, the area perpendicular to the our cross section. Since a square cross section, so perpendicular to this paper or this sheet, so in a perpendicular direction, it will be equal to h. So we have that h minus uh square equal to 0. So it will essentially give us uh is equal to will be equal to integration of 0 to h u of x dx. Now the tricky part is to find u of x. So what I did was I found out the equation of the straight line from at the exit. Okay, I assume the velocity profile to be a straight line, and if I take the along the x direction the x coordinate and along the y direction to be the velocity u, so I assume the equation of line to be of this form, right? U equal to mx plus c, where it is shown in the diagram that at x equal to h, v equal to v mean, and at x equal to 0, v equal to v max. Correct? So I have chose those conditions and substituted these conditions into my equation of line. Okay, So after doing the substitutions, I get Vmax equal to C, because x would be 0, then it will only be Vmax. Then Vmax is equal to C and V minimum is equal to MH plus C. Okay, where M is the slope of the line. So if I subtract this equation from this equation, I get V min minus Vmax is equal to MH. Okay, and then I get the value of M from this. Then I substitute the value of the slope in this equation. Okay, and from that I get the value of C. So my equation has this form. Is it same? Oh, it is a bit different. I guess it will be, I don't know, it will remain same, but let us see. So I get the equation of this form. Okay, so finally when I substitute the value of C and M in my equation of line, this one, I get U of x is equal to V min minus Vmax by H into x plus Vmax. Okay, is it clear to this point, Priyanka and Augustus?
Yes, sir.
Yes, sir.
Okay, then since I got the equation of my line in this form, which is essentially the velocity profile in this case, I substitute it in the equation UH is equal to integration of 0 to h ux dx. So I substitute the velocity profile here, I do the necessary integration, it will give us x squared by 2 and it will give us simply x. So I do the necessary integration, so I get UH is equal to V min plus Vmax by 2 into h. So since we know Vmax is equal to 2 V min, I substitute here Vmax is equal to 2 V min, since I've already given it, and then I get this is equal to 3 V min. So UH is equal to 3 V min by 2 into h. H will get cancelled out in both the sides. So we will essentially get V min is equal to 2 by 3 into U. And if you substitute the value of U, you get 2 into 15 by 3 would be equal to 10 meter per second. So is that clear? How did the integration?
Yes, sir.
Yes. Okay. Okay then. So Priyanka, I guess your approach was also correct. So thank you for letting us know a new approach. But essentially, as I already told, mathematics is like very beautiful. Our approach may be different, but the solution should remain the same. And since in this case you can clearly found out that our approach was different, but the solution was same. So you can use both the approaches. Okay, both Augustus and Victor, you can use both the approaches. That's fine.
Yes, sir.
Since the concept is correct. Okay. Okay then. Let us look into second final. It's the fifth question, I guess. Yeah. Actually, it's a very simple question, but a very conceptually interesting question. So let us look into the concept later, but solve the question first. Okay. In a steady flow through a variable duct, again, it is mentioned it's a variable duct. Say it can be of this form. Variable area. Okay. The downstream density is 1 kg meter cube. The velocity at a downstream only. Downstream is 1000 meter per second, and the area is 0.1 meter square. Okay. The upstream velocity is 1500 meter per second, and the area is 0.25 meter per second, 0.25 meter square. What is the density at upstream? So I guess I drew the diagram wrong. So it should be more like this. Okay. So they have told that if I take the inlet or the upstream as 1 and downstream as 2, then they are told that the inlet velocity is 1500 v1, a1 is 0.25 meter square, rho 1 is what we have to find out, v2 is 1000 meter per second, a2 is 0.1 meter square, and rho 2 is what is rho 2? 1 kg per meter cube. And told it is steady flow, we need to find out rho 1. I guess it's the most simple or simplest question of today's problem solving session. So please tell me the value of rho 1. It's very simple. I guess this is the first question in today's session where the density is also varying. And interestingly, density is what we are needed to find. So, yeah. Steady flow. Apply simple mass conservation. Yeah.
Sir, D.
D. Okay. So Augustus, do you get the same answer?
Yes, sir. 0.267.
Okay. So interestingly enough, both of you are correct. So it's a very simple, I guess the simplest question for today's session, right? Simple
Yes, sir.
mass conservation. So I guess, see, it's very simple, so I don't emphasize both of you to tell me. So it's very simple. You need to equate this. Rho A1 V1 is equal to rho A2 V2, right?
Yes.
So you get
Yes,
rho
sir.
1 will be equal to rho 2 A2 V2 by A1 V1. So it will be basically be 0.267 kg per meter cube. Okay. Okay. I would say it's a very interesting question, very conceptually, as I've already mentioned. So, just out of curiosity, can anyone of you tell me why this problem is conceptually very interesting? Just you can tell, like, whatever you may feel, why it is interesting. It's very simple, but yet it's very interesting.
So both area and density are varying.
Okay, it's hard to say. It's very appreciable that you rightly pointed it out. But what's the phenomenon that's occurring, or what kind of flows such flows are called, where both the density and areas are changing, or essentially why density is changing? What are such type of flows called?
Incompressible.
Incompressible. Then how density would change if it's incompressible?
Sorry, sir, compressible.
Yeah, rightly. Yes. Compressible flow. So such kind of flows are called compressible flows. So I don't know whether any one of you have taken a compressible flow course or either have studied about compressible flow in your fluid mechanics courses. So I'm just asking, have you read about compressible flow in your colleges, like, or have you at least learned about compressible flow?
So the total derivative of density must be equal to 0. The volumetric strain rate must be equal to 0.
For what?
For incompressible flow.
No, I'm asking about compressible flow. Have you learned about it, read about it, or?
No, sir.
Okay,
No.
that's fine. So see, in our previous questions, we had velocity in the regime of 3 meter per second, 18 meter per second, 30 meter per second at max, right? What is the velocity in this case? 1000 and 1500 meter per second. So do you know how to find out the velocity of, say, let's leave it. Do you know what do you mean by velocity of sound of a medium? Velocity of sound. I guess I've discussed this slightly in the first session itself, Professor Chakraborty also
Uh,
discussed. Yes.
Mach number.
Mach
Sir.
number.
Forget about Mach number.
Yeah, something related to Mach number, right? So ma was given by v by c, and c was essentially the speed of sound of that medium. Okay, speed of sound. So do you both of you have calculators near you? Like, since I do not have.
Yes, sir.
Okay.
Yes, sir.
So the speed of sound, and if you read compressor, you find out that speed of sound is given by gamma RT. Say for if it is room temperature and say it's air, so air for gamma for air is essentially I guess 1.4. The value of R would be 287 if I'm not wrong, and temperature, say room temperature, say 300 Kelvin. So could you please tell me the value of this? Oh, wait. Yes. Please tell me the value of this. Square root of 1.4, 287 into 300. Yeah.
So 347.19.
Okay. Again, tell me the value of, say I'm taking an inlet, 1500 by 347.19. What is it?
4.32. First one.
4.32.
Okay, second one, 1000 by 347.12. 19.
2.89. 2.88.
2.88. See. So I guess you can know that both are in the compressible flow regime, right? Mach number is very high. It's greater than 1. May not be hypersonic, but it is supersonic. So I guess you have read about, say we had our equation, right? A1 V1 is equal to V2 when density was constant. Essentially where the flow was incompressible. In the incompressible flow regime, you had the volume flow rate to remain constant, right? Q1 equal to Q2, right? So it would give A1 V1 would be equal to A2 V2, essentially. So if say we had the same, this would be a nozzle in this case, right? Since the exit has a lower area, lesser area compared to the inlet, this is essentially a nozzle for a subsonic case. Interestingly, for a subsonic case, right? Say if our inlet area is inlet area is 0.25, and I have given the inlet velocity as 10 meter per second, very much within the supersonic range, right? Within the subsonic range. And A2 I have given as, it is given as 0.1, right? 0.1, and V2 is unknown. Now could you please find V2? What would be V2? 0.25 into 10 by 0.1. So I guess it's very easy again. This will be 100. So essentially 25, if I'm not wrong, right?
Yes, sir.
So what do you observe? For a subsonic case, if the area is reduced, because A2 is less than A1, right? A1 I have given as 0.25, A2 is given as 0.1, right? So if the area is reduced, the flow velocity has gone up, right?
Yes, sir.
Yes, sir.
Yes. But in this case, you can see, even if area has gone down, the velocity has also gone down, right? Interestingly enough, it's different from
Yes.
what we usually
Yes, sir.
study for subsonic case, right? So what do you think has essentially caused this reduction in velocity even if the area is reduced?
Change in density.
Yes, it's a change in density. The change in density is appreciable, very much appreciable in a supersonic case, which overcompensates the usual flow pattern that we can observe in subsonic case, and which essentially causes a reduction in the velocity even if the flow passes through a nozzle. And that's why for a subsonic case, for a supersonic case, this acts as a diffuser. Okay. That's why I told this problem is very interesting, because you can clearly see the difference in the velocity regime, right? 1500 meter per second, 1000 meter per second. The one who has made the question, this question, could have easily written it as 15 meter per second and 10 meter per second, but instead they have correctly, conceptually, very correctly, accurately they have written it at 1500 meter per second and 1000 meter per second. See the beauty of the question, right? Even the one who has written the question is like knows what is the concept, underlying concept within the this question. Okay, that's why I told this question was very interesting. And like eventually, like if you, this course is limited to the dynamics of the fluid flow, so this course will not go up till the compressible flow regime, but still, like if you're interested, you might read the compressible flow in your later part of the course of your college, of your BTech. So I encourage you to learn about it, right? So that's why this was interesting. So was it interesting? I'm asking both of you, was it interesting? An interesting concept?
Yes, sir. Yes, sir.
Yes, sir.
Thank you. Yes, thank you. Okay, then we reach the last question. So today, okay, for 4 questions, 6 to 9. So I'll read the question. The fluid in direct contact with a stationary solid boundary has 0 velocity. Okay, there is no slip at the boundary. No slip at the boundary. Thus, the flow over a flat plate adheres to the flat surface and forms a boundary layer. Again, I have discussed about boundary layer in my previous class, I guess. So, the flow ahead of the plate is uniform with velocity v is equal to ui cap. Basically, in the vector form they have denoted. The velocity distribution within the boundary layer u in this range along CD, this line is approximated as u by u is equal to this. This is the velocity profile at the exit. So you can essentially write it as mu of y would be equal to capital U sine of pi by 2 y by del. So this is the question, and width is given, perpendicular to the paper is given by W. Okay, and they have also shown us the control volume. This is the control volume. Okay, so given this idea, the mass flow rate in the control volume across the section AB is given by, so you need to find the mass flow rate, and for simplification you can take the flow as steady flow. Okay, given this, please find the mass flow rate through section AB. Or essentially, I will simplify the question even further. You need to find mass flow rate to all the 4 sides of the control volume. Find the mass flow rate and tell me what would be the answer. Okay, basically m dot AB equal to m dot BC would be equal to m dot CD would be equal to, and m dot AD would be equal to. These are the 4 questions. Okay, so tell me the answer. It's very simple. Again, it looks difficult, but since they've already pointed out the control volume, so it's not that difficult now. We just need to do the integrations at the inlet and exits and find the mass flow rate. Simple mass conservation. Okay, let me solve the first one. Could you please tell me, yes, could you please tell me the mass flow rate to AD?
Sir, rho u delta W.
Okay, AB, right?
Oh, sorry, AD, sir, is 0, sir.
Yes, thank you. AD is 0. Why?
It is solid. There is no
Yeah.
water flow across it.
Yes, no penetration, right? So they have not mentioned any porosity, so you can ideally take it as no penetration. Okay, because of that's why m dot AD is equal to 0. At least one question is solved. And what you are telling for MAB, right? Rho u delta W.
MAB, sir, rho u delta W.
Okay, this is the first answer. Okay, Augustus, did you get the same answer for MAB, m dot AB?
No, sir. I'm still working on that.
Sure, no problem. That's fine. Okay, Priyanka, I encourage you to solve the remaining parts, m dot BC and m dot CD, and let's discuss at the last, like what are the correct answers. Okay, so you can do the rest of the part, rest of the mass flow rates also.
Yes, sir. I am getting rho u del w, sir.
Okay, so it's correct. Yeah.
Yes.
Now could you please, and since we already know the two, you need to find the other two, right? M dot BC and M dot CD. So you can quickly find the both of them and just tell me the answer. Similar to the pipe flow case, the exit has CD has a velocity, given velocity profile, so you need to do the proper integration, choose the limits wisely, and okay. See here, like after the solution I will tell choice of the given control volume simplifies the problem a lot, because you get upper limit for your integration. If in a case if you have chosen a different velocity control volume for the same case, the problem would have been a bit difficult. I'll show you, but right now you can go ahead and tell me the answer. M dot,
Sir, m dot CD is equal to rho u del w, sir.
M dot CD is
Rho u del w, sir.
rho u del W. Did you do the integration? This?
Sorry. Then it will change. It is 0, sir.
How that would be 0? Integration of sine would be minus cos, and if you put the given limits, upper limit and lower limit of integration, I don't think you would get it at 0, and logically also, like you can clearly see there is a mass flow
Yes.
rate out of CD, right? So you will have some non-zero value. You do the integration, okay? Then tell me the answer. Yeah.
Yes, sir. Sure.
So
Yeah.
I got M dot mass flow rate across CD as option C.
Option C. Oh, this. Okay, interesting enough. Okay, you get it as 2 rho u delta W by pi. Okay, then I guess M dot, what's remaining? BC is very simple now. Could you please tell me what is M dot BC?
I got it as rho W U delta into 1 minus 2 by pi.
Let me check. Is it an option? M dot AD is 0, so this is the right answer. And you get, okay. So, yeah. So, let me, like, since we are short of time today, so let me say that both these are correct. So Augustus, you can do the integration. You can find out m dot ct to be 2 rho u delta w by pi. Okay.
Sure.
You did I okay. Again,
So the same
yeah,
the same velocity profile, the same velocity profile, and the limits to be integrated between is 0 to del, no sir?
0 to del.
For
Yeah.
CD.
Yeah, 0 to del. Since again, okay, let me show the solution, because others who will watch the video later could get some help. So please bear with me, just for few minutes, okay?
Sure.
Thank you, Priyanka. All your answers were correct. Let us go through the solution once, okay? This is the geometry that we are given. This is the boundary layer. Augustus, do you know the concept of boundary layer?
Yeah, yes sir. I know.
Okay, very good. So that's very good that both of you know about boundary layer. Okay, so, and width is given, perpendicular to plate is given by w, and this since see, the beautiful part of this question is they have given us the contour volume. Say we could have chosen, if it was not given to us, we could have chosen the contour volume as let me show as a red color, as a blue color. Say we could have chosen a contour volume as this one also, right? Oh, sorry. We could have chosen the contour volume as this one also, right? This blue box that I'm drawing right now. So could any one of you please tell me what would have been the problem in this case? This is also a correct choice. It is not wrong. Velocity is defined at the inlet and exits. We are keeping the inlet and exit of the contour volume as the inlet and the exit of the geometry. So it is correct. But what would have been an analytical problem in this case?
Sir, across CD, the velocity, it will vary.
Yeah. Plus, yes, because
We don't know the u infinity also.
no, u infinity is same. It will same, but you essentially you do not know the you, even if you know h, say if it was chosen h, say you took it as h, your velocity profile is not available for this region, right?
Yeah, yes.
So this would have been a bit difficult. You would have to do, you would have had to do an integration from here to here, say 0 to del, plus an integration from here it is del, right? 0 to del, plus an integration from del to h, where with a velocity profile u infinity. Since across the boundary layer, the velocity will essentially be u infinity as an approximation, okay? Because you know that across the boundary layer it is not directly u infinity. It was actually 0.99 of u infinity, but even if we disregard the contribution of or the loss of mass flow rate because of ignoring that part, you can directly take it as u infinity. So you have to take the integration from del to h again with u infinity as a velocity profile, right? So this would overcomplicate the problem, right? This would have overcomplicated the problem. But since, and again you would have had an unknown h, like this is a parameter that you will essentially choose. It is not given in the problem. So this would have been a problem, and overcomplication of the simple problem. So essentially what they have done is that given a contour volume that exactly ends at the boundary layer at point C. So this would basically mean that CD is equal to delta, right? And it is because of that only you are getting a upper limit of integration as delta. Am I right, Priyanka?
Yes, sir.
Yes. Augustus, I guess you have also chosen the same approximation, because that by that only you have evaluated the mass flow rate at AB, right? You need to know the height
Yes,
h,
sir.
and that will be equal to delta.
Yes, sir.
Now I guess now you see why it is very important to choose the right contour volume to simplify our problem, right?
Yes, sir.
And essentially,
Yes, sir.
if in the lectures also, I guess sir would have pointed out and another choice that would be a control volume which has one of its edge as the streamline. that again simplifies the problem further because there is no mass flow rate across the streamline. Yes, that again simplifies the problem. So keeping this idea, so let's quickly go to the derivation. So velocity profile is given by mass conservation. You write the full equation. The first term will be 0 because the flow is essentially steady. So you get the second part. So that will be equal to 0. Then if we take rho as a constant, then we can essentially write VR dot n cap dA is equal to 0. And this would essentially give us m dot cd, that whatever is exit flow mass flow rate at the exit minus the mass flow rate at the inlet would be equal to 0. So what are the exits? It is CD and BC, right? So m dot CD plus m dot BC minus m dot AB would be equal to 0. And m dot AB will be easily get as rho u delta W because it's simple. Rho is the density, A is the area would be equal to W into delta, and U is the uniform velocity profile. So you will get as rho u delta W. M dot CD you will have to do the integration. So rho is out of the integral because it's constant. So U sine pi by 2 y delta dy W. So you do the necessary integration with the proper integration limits. So after substituting the limits of integration, you get the value of m dot cd would be equal to 2 rho w u delta by pi, which is m dot cd. Okay, and finally we have from this equation we can find m dot bc would be equal to m dot ab minus m dot cd. Okay, you get it, Augustus, how we got this? M dot bc is equal to m dot ab minus m dot cd.
Yes, sir. Yes, sir.
Yes.
I got it, sir.
Yes. Finally, we substitute the values of m dot ab, that is rho u delta w minus 2 rho w u delta by pi, and finally get m dot bc equal to rho w u delta 1 minus 2 by pi. So, is it clear?
Yes, sir.
Yes. And Priyanka, I guess you use the same approach.
Yes, sir.
Okay. Okay then. Thank you to both of you. I am really sorry I crossed the time limit, but also we started the session a bit late, so I guess we compensated that with the extension. But I'm really sorry again if I extended beyond the given time limit. So thank you for bearing with me, and if you have any doubts, you can ask in the next session. I encourage both of you to join the next session. It will be very interesting because we will be dealing with the linear conservation of linear momentum and even more complicated problems. So thank you again to both of you. See you in the next session.
Sure, sir.
So,
Thank you very much, sir.
Okay,
Thank you,
sure. Yes, Priyanka. Yes.
so next session Sunday or Friday?
It is Friday. I guess they mail you, right? It is on Friday.
Okay, sir.
Because of okay, let me be clear. Because of certain issues, I shifted the session from Sunday to Friday. So that's why we are having this change. I guess they mail you also regarding the change in the session. So I guess they mailed it yesterday night, right? Regarding today's session.
They mailed that today there is a session, sir.
Okay.
Regarding the change, I didn't know. That's
Okay,
why.
okay. I'm sorry. Okay, let me remind you. They mailed it, right? They mailed it that today's session. So my session, all sessions will be on Friday from now on. Okay, remaining session will be on Friday itself.
Hello, sir.
Yes, yes.
Okay, sir.
Remaining sessions would be on Friday. Next Friday we will meet again on next Friday. Okay, for week 10.
Yes.
Okay,
Week
sir.
10 concepts. Okay then. Thank you. Thank you to both of
Thank
you.
you.
Thank
Yeah, yeah, sure.